Dantec Dynamics webinar. By way of introduction, I am Graham Hassel, Group Manager for Dantec Dynamics UK, with 39 years of experience in fluid dynamics and Dantec systems, and I specialise in hot wire and laser anemometry. My colleague and co-presenter, Dr. Ivan Zadrazil, is a Senior Engineer and PIV Product Specialist at Dantec UK. He has 5 years of experience at Dantec and 10 years in fluid dynamics research at Imperial College, specialising in PIV and LIF. By way of housekeeping, your microphone and camera will be turned off during the presentation. And if you have any questions that occur to you during the presentation, please do not hesitate to post them in the chat section and they will be addressed at the end. The final point I will make is that the webinar will be recorded and the recordings will be made available to all participants. Today's webinar will introduce you to our many measurement techniques with a focus on the Edu PIV system. First part of the webinar will give a brief outline of the company's structure and history, and then go on to give some insight into the broad range of measurement systems that we produce. To complement this introduction, I will give you a few typical examples of where the techniques have been used, which I hope you will find interesting and encourage you to subscribe to future Dantec Dynamics webinars. The duration of this section will be approximately 15 minutes. The focus of today's webinar will cover the recently introduced Edu PIV system, which my colleague Ivan will explain in some depth, together with a brief introduction of the principles behind the PIV technique. Specifically, he will cover the Edu PIV concept, the main components, software, and give some measurement examples with an online installation demonstration. The duration of this section will be approximately 30 minutes. In brief, Dantec established themselves over 50 years ago and are a global company engaged in the supply of measurement systems for fluid and solid mechanics research. Our head office and production capability is located in Denmark, and we have subsidiary offices in the UK, US, France, Germany, and Japan. In addition to this, we have 30 distributors around the world to give a truly global sales and support capability. This support is provided by over 100 people, all of whom have advanced qualifications, which in many instances is complemented with significant experience in the application of advanced measurement techniques. Next slide, Ivan. This slide shows the evolution of Dantec Dynamics from 1947, where our first electronic device produced was an oscilloscope known as the universal indicator. A very advanced instrument in its day, although now it is more noteworthy for its weight at an awe-inspiring 65 kilograms. With this background, it was a relatively simple step for us in the late 1950s to make one of the first commercially available hot wire anemometry systems to satisfy the increasing demand for turbulence measurements within the fluid mechanics community, which we have continued to develop to this day. One area within fluid mechanics that wasn't satisfied by the hot wire technique was that of non-invasive measurements or measurements in hostile environments, which led to the adoption of the laser Doppler anemometry technique, which non-invasively measures the velocity at a point defined by the intersection of two laser beams. In 1984, a spin-off from the LDA called PDA or phase Doppler anemometry, or in some places particle dynamics analysis, was developed, where not only could the velocity of the particle be measured, but also the size, which has proved to be of great use to many industries and areas of academic research. examples of which are fuel sprays and medical inhalers, where the droplets are small, velocities high, and the density of the sprays is also high, which makes other methods of sizing and velocity measurement difficult or impossible to apply. A little like hot wire anemometry, one application that could not be addressed by LDA was the measurement over an area or volume at an instant in time. To an extent, this can be addressed with a rake of hot wire probes or laser anemometers, although the laser option would incur a significant cost. This led to the development of particle image velocimetry, or PIV, in the mid-1980s, where images were recorded on wet film, processed and then analyzed to give particle displacements over an area. This required great patience and introduced severe limitations with respect to observing how a flow develops over time. The explosion of usage of the technique really started in the late 1980s with the advent of CCD cameras, which gave the possibility to observe the time history of the flow over significant fields of view, which when combined with dual cavity lasers gave researchers a tool to use in the lab. One other significant development for Dantec occurred in 2000, where we acquired a company that specialized in solid mechanics, which included digital image correlation and non-destructive testing chirography systems. The digital image correlation system enables the user to make dynamic deformation measurements in 3 dimensions via an imaging technique based on a pair of cameras similar to the stereo PIV technique. In fact, we have users that are combining both the PIV and DIC techniques to observe deformation of an object in a flow. This approach is sometimes referred to as fluid structure interaction, or FSI. In more recent times, Dantec has developed microscale PIV systems and advanced volumetric PIV systems, which can give an insight into the most complex of flows. This broad range of products is seeing continuous development and refinement via our in-house developers and collaborative partnerships with many leading academic establishments around the world. So, by way of a brief summary for fluid mechanics, we have the following techniques. Hot wire or constant temperature anemometry for the measurement of velocity or turbulence at a point. Laser Doppler anemometry for measuring point velocities in 1, 2, or 3 dimensions non-invasively. Particle image velocimetry for measuring velocity fields in a 2D plane with 2 or 3 velocity components. And with the recent developments of the PIV technique, which have led to the capability to measurement of all 3 velocity components in a volume, sometimes referred to as 3D 3C. Which means 3 dimensions and 3 components of velocity, using 3 and 4 camera systems, commonly known as volumetric PIV. We also have laser-induced fluorescence-based techniques for determining concentration and temperature in a plate, along with micro PIV, which is a customized PIV technique for liquid flows, typically used on micro-scale channels. We also have an array of combustion diagnostics tools, the most commonly used being based on laser-induced fluorescence, where it is possible to identify combustion species such as OH, NO, and CO, and from this obtain qualitative data and concentration. Another area of interest is the temperature measurement of soot particles in combustion processes, which can be done by observing the incandescence created by soot particles when entering a high-power laser field. Chemiluminescence occurs in some chemical reactions where electromagnetic radiation is emitted in the ultraviolet, visible, or infrared, which can be observed to give information about the reaction process. The equipment required is the same as for LIF, with the exception of no laser being required. Rayleigh scattering is a planar gas temperature measuring technique which uses high-powered lasers to generate Rayleigh scattering. PDA, or phased Doppler anemometry, is widely used, as I mentioned earlier, in the field of combustion, where the drop size of fuel from a fuel injector has been very closely studied, which has led to developments which have been instrumental in reducing the emissions of vehicles. PDA measurements have also been complemented in less dense sprays by the shadow technique, which measures size, shape, and velocity by observing backlit particles' shadow on a camera. We also have an array of supporting products, one of which is digital image correlation, which I mentioned earlier, which is capable of performing a non-contact 3D measurement of a surface, which increasingly is being used in the fluid mechanics measurement environment to determine how an object moves under load from a fluid. Dantec are also involved in non-destructive testing and have developed a non-contact method that can detect voids and delaminations in a structure by taking an image of the surface after it has been bent, heated, or pressurized. This technique is unlikely to be of great relevance to your immediate requirements, but it is an example of our diverse product range and capabilities. Somewhat closer to home and of increasing relevance to all of us is room or cabin air movement, which Dantec have been involved with for in excess of 30 years. The system produced, known as Comfort Sense, is based on the constant temperature anemometry principle and gives accurate measurements of velocity in the range of 5 centimeters per second to 5 meters per second. This custom designed solution is based on a 2 millimeter diameter spherical sensor, which will measure air velocity over the whole surface of the sphere, which is required for room air movement, where the direction of the flow at low speeds can change very quickly. Many of the aforementioned methods will be covered as part of the Dantec webinar series. To conclude my part before handing over to our PIV specialist, this slide shows where each of our techniques are used during the development of a car. Starting with the comfort sense at the top left, we have a mannequin equipped with spherical sensors I mentioned earlier, which will enable the car maker to produce a comfortable and well-ventilated environment for the driver and passengers. We then go on to PIV, where we look at the aerodynamics of a vehicle to reduce the drag and ensure stability at high speeds. Bottom left shows some spray imaging used to develop windscreen and headlamp washers to ensure that the optimum spray pattern and droplet size is created to give the driver a clear view ahead. The central picture shows LDA and PDA systems, which are used for engine development, cooling requirements, aerodynamics, and other internal and external flows. The image in the bottom right shows jet mixing and measurement of concentration of OH radicals during combustion via an LAF technique, which uses the same or adapted lasers and cameras as used in PIV systems. Other quantities such as concentration, presence of combustion products, soot, temperature, etc., can be measured using this technique. The mid-right picture shows an example of a robotized non-destructive testing system which can detect defects in panels. This is currently used extensively in the aerospace industry, where defects need to be identified quickly for safety reasons. And with the increasing use of composites, it is now being used in the automotive industry. Finally, and my favorite, a hot wire probe was used to develop an understanding of the airflow around a brake disc. This was used directly for the development of a very large brake disc for a certain high-performance car company. I think I can safely add here that making a 2,200 kilogram car accelerate to 320 kilometers an hour is relatively simple, whereas producing a set of brakes that will stop it more than once is not so easy. I hope you can see from this first section that Dantec Dynamics provides comprehensive measurement systems for many fluid and solid mechanics research and development applications. I'll now hand you over to my colleague, Dr. Ivan Zadrazil, who will take you through the Edu PIV system. Thank you for your attention.
Thank you, Graham. So in the second part of this webinar, I'm going to be talking about educational particle image velocimetry system, or shortly Edu PIV. So initially, let's just talk about what do we want to measure. So on the left-hand side, you can see a plane which lands, and this is actually an example of fluid dynamics, because the plane obviously flies through a viscous air, and the movement of the air is actually moving the air left and right, and the pilot is actually struggling with landing. However, we don't really see the movement of air or the forces exerted by air on the plane. We are just guessing. We actually can just see the outcome of it, which is quite dramatic landing. Bottom right, we can see hydraulic jump, which is a flow over an obstacle. And again, we can see sort of what's going on from the free surface of the liquid, but we don't really have any understanding of what's going on inside the liquid, how the velocity fields look like, and what's going on with respect to mixing and so on. In the middle, there's an example from heat transfer, so mirage. This is an effect caused by the change of refractive indices of air as it's heated up close to the surface. Then we have combustion, and finally on the right there's an example of PIV raw images where we actually can see the flow structures. So in general, it's seeing the invisible. That's what these measurements are about, understanding the invisible, so fluid mechanics in general, and using this knowledge for design and engineering. Right, so what is PIV and how does it work? Well, PIV is an optical technique for measuring the instantaneous velocity over an area, and it's based on a displacement of seeding particle. So let's imagine that we have a flow of gas or liquid. However, the flow is invisible. So we can add some seeding particles, and these are added to actually track the flow structures. These can be typically in gases droplets, so for example 1 to 3 microns DEHS droplets, or in liquids these are solid particles, for example 10 micron hollow glass spheres. However, we still cannot see them. So what do we need to add is some kind of illumination. So typically with standard PIV systems, we use double pulsed lasers, and the laser beam is expanded to a 2D sheet to provide a planar illumination, as you can see hopefully on the animation, which should show a double pulsed laser. And the 2 pulses will give us delta t, so this is the time in order to calculate velocity later on. And these lasers are typically either low speed or high speed. Low speed are, for example, 15 Hertz, and the YAG, which is neodymium doped yttrium aluminum garnet. These typically emit at 532 nanometers, or they can be high-speed lasers, also double pulsed, which is neodymium doped yttrium lithium fluoride. They emit at 527 nanometers, and typically the native emission frequency is about 1 kilohertz. Right, so let me pause the animation during one of these pulses. These pulses are typically 10 to 100 nanoseconds long, so they're actually very short, and it's used as a flashlight pretty much to freeze particles movement. So there's no motion blur when these very small particles are imaged. So we have illuminated the particles, but then we need to actually collect the light from the particles. So we used camera with a global shutter. This camera is equipped with a lens, and it's used to capture the scattered light from particles. And there are 2 different modes in which we can operate. It's a single frame. This would be just, for example, 15 Hertz camera. So we collect standard frames which are separated by 1/15 of a second, or double frame images where we acquire at exactly the same frequency, but each image consists of two sub-images or frames. And these can be separated based on the duration of the two double passes, or the delta t, which is the time between the two double passes. And this can be as short as 150 nanoseconds. And also we have here something which is called measurement volume. So this is the volume over which we measure. So we are producing 2D laser sheet to illuminate an area. However, that has some kind of thickness. And this thickness is actually quite important, especially when it comes to different types of PIVs, or when it comes to three-dimensional flows, because flows are not two-dimensional, they are three-dimensional. And we want to illuminate the particles for long enough so they are illuminated during the first frame and the second frame. So typically the measurement volume is with standard PIV is defined by the laser sheet thickness, or in micro PIV or volumetric PIV is defined by the camera depth of field. And what it is in PIV, it's about less than 1 millimeter. In stereo PIV, it's less than 5 millimeters, and in volumetric PIV, it can be tens of centimeters. So now we go to the actual recording. So during the recording, we collect a series of single or double frame images. In this example, we are recording a series of double frame images. And just for imagination, information, if you would operate the system in a single frame mode, the maximum measurable speed would be about 1 millimeter per second. That's actually not a lot in most of the fluid dynamics measurements. But in double frame mode with the same camera, we can measure speeds of exceeding 1,000 meters per second. So that actually is going to cover pretty much any kind of experiment that we might be interested in doing. So once we collect the images, we go on to processing, so PIV processing. And in this case, images are divided into so-called interrogation windows. These are small subsections, and typically this can be, for example, 32 times 32 pixels. And then we calculate the average displacement of all the particles within this interrogation window, as you can see on the slide. And this is actually the displacement, so the length, which is then used to together with the time between the two laser pulses to calculate velocity. So the displacement is then calculated using 2D cross-correlation based algorithms. And we use an adaptive PIV, which is the most advanced algorithm on the market, where you adapt the size of the interrogation window based on local seeding density. And you also adapt the shape of the interrogation window based on local velocity gradients. So finally, the velocity vectors are calculated for each interrogation window with a sub-pixel precision. What do I mean by that? Is that the particles, they don't need to move pixel by pixel, but what we can do is actually calculate sub-pixel displacements, and we can very accurately calculate even 1/100th of a pixel displacement. And with decreased accuracy, we can also calculate 1,000th of a pixel displacement. And what we get is a velocity vector map, which can be shown graphically or as a table with X, Y, U, and V coordinates. And finally, we can extract additional parameters from the velocity vector map. For example, Q criteria, streamlines, vorticity, different moments, stresses. We can extract pressure as well, energy content. We can do different correlations. We can calculate velocity fluctuations, extract velocity profiles, acceleration, shears, and many more. Right. So hopefully that gives you some understanding how classical PIV works. So here on this slide, I'm just going to talk about what kind of different PIV techniques do we have. So let's start with Edu PIV and Edu Stereo PIV. This is an entry-level PIV, which is specifically designed for education purposes. And hardware-wise, you have either one or two cameras. We do not use lasers. We use safe LED illumination, and of course, LED sheet optics to illuminate the particles. And then there's a PC and laptop. And during the typical measurement steps, we do single camera calibration. We image we record some images and then do some image pre-processing to increase the signal to noise ratio. Then we do PIV calculation, and finally we can present the data and do some statistics. On the other hand, the second part is going to be on research-grade PIV systems. So let's start with 2D 2C PIV. 2D means that we are measuring in a plane, so 2D, and 2C that we are measuring two velocity components. And standard 2D 2C PIV is a robust and mature technique, which is suitable for a wide range of applications. And similar to Edu PIV, we are using a camera. However, contrary to Edu PIV, here we used PIV lasers. As I mentioned before, they can be low speed or high speed. And of course, they're equipped with light sheet optics to generate this 2D illumination and a little bit more powerful PC. And the typical measurement steps are identical to Edu PIV. So initially we do camera calibration, we record some images, we pre-process them, we apply PIV algorithm, and then we present the data or do some statistical analysis. Stereo PIV is a 2D 2C technique. So here the 3C means that we can measure all three velocity components in a plane, and it's a good trade-off between 2D 2C and 3D 3C PIV techniques. So over here we can relatively quickly measure all three velocity components in a plane. And hardware-wise, we have two cameras. We use exactly the same laser as with standard PIV, equipped with light sheet optics. We use slightly more powerful PC, and the typical measurements are a little bit different. Initially, we need to calibrate two cameras, which is quite different compared to single camera calibration. We record images, pre-process them, then we dewarp them because they are distorted perspectively. Then we calculate 2D PIV velocity vector maps, and then we, using the calibration from the two cameras, we recombine the 2D velocity vector maps to get a 3D velocity vector map. And finally, we present the data and do some statistics. And finally, here we have volumetric PIV, which is a 3D 3C technique. So we measure all three velocity components in a volume, and it's a potential game changer. However, this technique is quite complex, and typically one needs to build an experiment around this technique. And hardware-wise, we use multiple cameras, typically 4+. The more cameras, the better. We use the same type of lasers as in the previous cases. However, we tend to use more powerful lasers because we are not expanding the laser beam into a sheet, but into a volume. And typically we use two different PCs. One is used just for acquisition and another one for processing. And the typical measurement steps is calibration of 4 cameras and setting it up, image recording and pre-processing. Here, in the next step, we do volumetric image reconstruction. So from the planar recordings, we reconstruct a 3D space with particles. And we use this reconstructed 3D space for volumetric PIV calculation in order to get all three velocity components in a volume. And finally, there's some data presentation and statistics. So the research-grade PIV systems, they use class 4 lasers. This is the highest class, and as such, there are some safety requirements that needs to be met. And the reason for this is that since it's a pulsed laser, and the pulse is very short, typically 10 nanoseconds, and typically the energy per pulse is about 200 millijoules, then it means that the peak power is up to 200 megawatts. 200 megawatts, which is expelled in 10 nanoseconds. So there's a mandatory use of laser safety goggles. Users have to undergo laser safety training. And of course, the systems are typically operated or should be operated in controlled environment, which are laser enclosures. On the other hand, Edu PIV uses LED illumination, so there is no problem with safety. So what is the background for Edu PIV? Well, in general, very few undergrads have hands-on experience with PIV due to cost, availability, and laser safety concerns. Because typically undergrad students in the country where I'm based, United Kingdom, they are not allowed to use class 4 lasers. So once they start working on their research projects as a PhD students or postdocs, they don't have really any prior experience with this sophisticated technique. So the idea is to create a pipeline of experienced undergrads with knowledge of PIV, and also to use Edu PIV for training of even more experienced PIV users. So what would Edu PIV allow you to do? Well, PIV or Edu PIV allows you to do time-resolved PIV measurements, typically in undergrad fluid mechanics labs. It uses safe LED illumination. There are no lasers, so there's no concern when it comes to safety. It contains full version of Dynamic Studio to provide the students with real-world PIV experiments. And it also comes with a predefined experiments and instruction guides. And one of the things that it actually comes with is a 3D printed nozzle that can generate a simple that can be used to make a simple experiment. However, this 3D printed nozzle can be exchanged with different nozzles and expand the potential of doing different types of measurements. So the main goal for Edu PIV is to provide hands-on learning for undergrad and graduate students prior to operating larger scale laser-based PIV systems that are typically used for research. So how does the Edu PIV hardware look like? So initially, let's start with a camera. We use FlowSense USB 2 M165 camera. As the name suggests, this camera can be operated at 165 frames per second in a single frame mode, and it's a 2 megapixel camera. This camera can be also operated in a double frame mode. However, for that case, you would need a double pulse laser. So it wouldn't be Edu PIV system anymore. It uses a USB 3 interface, so there are no frame grabbers, and you can use it just with a laptop. And I often use Edu PIV with the laptop from which I'm doing this presentation. And of course, the camera is equipped with a lens. When it comes to the LED illumination, it's one which is equipped with fiber light sheet optics. It provides a continuous illumination, so the illumination cannot be pulsed. It's very simple, switch it on, switch it off, and adjust the power using a knob. The light sheet divergence angle is about 37 degrees, and the maximum power is 150 watts. Yeah? So you can compare it to the peak laser power, which is 20 megawatts. As I mentioned, the Edu PIV comes with a simple experiment. The core of this experiment is a controllable smart pump, which can be used in different operation modes. And these are constant flow, pulsed flow, or periodic flow. And also what you can change is the flow rate from about 0.2 to about 0.5 liters per second. And this pump is connected to a 3D nozzle, which contains a number of flow straighteners to give a flat flow profile at the exit. But there's an option that the students can print their own 3D nozzles, exchange it using a flexible boot. So there's a flexible boot connection between a 3D printed nozzle and a pump, and just check whether the performance has increased or decreased. And finally, there's a water tank. So we are doing the measurements in water. The dimension of the water tank, just for information, is 80 times 35 times 40 centimeters. And everything is actually on a support frame. And the entire Edu PIV can be very easily mounted in about 15 minutes. So of course, as I mentioned before, the Edu PIV comes with a full version of Dynamic Studio. So it contains a full suite of PIV algorithms, not only adaptive PIV, but also a little bit more historical algorithms such as cross-correlation and adaptive cross-correlation. algorithms. It also contains a complete image processing library. So the goal here is to actually increase the signal to noise ratio. So if you do some PIV recordings, initially there can be quite a lot of noise, and Dynamic Studio is pretty much a powerful image processing software. So it allows you to remove any kind of noise and hence increase the quality of the final velocity vectors calculated. So it contains a lot of tools that can be used by either basic or more advanced students, or starting or more advanced students. And they will get a real world experience of how PIV measurements are done. In the case there is a pandemic, for example, Dynamic Studio also contains a synthetic data generator. So students can generate synthetic PIV images. They can simulate for simulated experiments. This can be 2D, 2C, stereo PIV, volumetric, pretty much anything with any configuration, with added noise and so on. And this can be used to learn actually how to process these data. Edu PIV comes with a single license. However, initial analysis licenses can be purchased. And as an example, this would be a network license where the student can connect to a server and do post-processing or PIV processing from home on their laptop. Right. So Graham mentioned that I'm going to show some online installation. So the Edu PIV system comes with an online video installation that can be accessed online. It's about 30 minutes long, so over here is slightly speeded up. As you can see the animation on the left. It's separated into 4 parts. In the part 1, we go through the hardware setup, so how to connect everything. In part 2, we explain how to do the measurements. In part 3, we go through the PIV analysis, including including image pre-processing. And finally, in part 4, which at the moment what we are showing on the animation is part 3, but in part 4, we extract some additional information out of velocity vector maps, such as velocity profiles, Reynolds stresses, vorticity, and so on. And of course, the system comes with a hard copy installation and processing manual where we go through the hardware setup and measurement procedures step by step. So how do the Edu PIV measurements look like? On the left-hand side, you can see a video of PIV measurements. So you can see the nozzle, which generates a pulsed flow. So you can see a jet being expelled from the pump, and then there's a period of time when nothing really happens. You can see the LED illumination and the particles. And on the right-hand side, they have already processed PIV results. So these are instantaneous velocity vector maps. And you can see that there's actually a stream of a flow from the nozzle, and there are some toroidal vortices on the side. And these instantaneous velocity vector maps can be further processed to extract some additional information out of it. Right. The Edu PIV system also comes with lab courses that we are continuously working on. And in this example, it's a flow rate measurements of Edu PIV pump. Yeah, so how to actually measure flow rate of the pump using a PIV system. And the idea of these lab courses is to introduce PIV to new users, to ease the academic workload. So the academics don't need to actually prepare these lab courses, and to teach all aspects of PIV experiments. So from setting up, measurements, processing, but also the use of PIV data. Because, well, PIV is a tool, actually, it's a research tool. So the final goal is not to generate some velocity vector maps, but to extract something out of it. And in this example, the goal is to extract flow rate, so a single number out of all these measurements. And on this image, you can see Edu PIV, Fluid Dynamics lab with 4 Edu PIV systems in Sun Yat-sen University. So in the first step, we have an experimental setup. So this is the adjustment of the LED sheet and focusing of the camera onto the particles. The second step during the lab course is the actual measurement. So it's maybe adding more seeding particles, adjusting the acquisition frequency of the measurements. So Edu PIV can run up to 165 frames per second, and then taking a number of images. And the question is, how many images should we take maybe? Then the measurements are over, and we turn to Dynamic Studio. And here we start with image pre-processing. So this pretty much what we are trying to do is to reduce noise. So in this example, I subtracted background, but we also generated a mask. So we mask out areas where there are no particles. For example, where the nozzle is located. The next step is PIV processing. So for example, one can use adaptive PIV to calculate velocity vector maps. And as I mentioned before, there are some interrogation windows. If you recall, they can be 32 times 32 pixels, but they can be smaller. And pretty much the spatial resolution is a function of the size of the interrogation window and the overlap of these interrogation windows. However, the smaller the interrogation window, the more noisy the results are. Yeah, so in PIV processing, the goal is to find some balance between spatial resolution and accuracy. However, Dynamic Studio also contains a number of filters that allow you to filter out noisy data and to remove spurious vectors. So spurious vectors are vectors that are wrong. Yeah, they point in non-physical directions. In the next step, in order to extract or to get a flow rate, we do some statistics. So in this case is averaging over time. So we generate time averaged velocity vector map. And the question here is, well, did we actually acquire enough images to have statistically converged data set? And this is also what the students can check. Finally, pretty much finally, we need to actually extract a velocity profile close to the nozzle. And the question is, well, should it be U velocity component? Should it be V velocity component? Or should it be product of these two? Well, it should be the product. And once we have velocity profile, what do? Well, we can import it into a third-party software, and using this formula, we can integrate and get a volumetric flow rate. And this can be done in, well, as I mentioned, third-party software, for example, Excel, Octave, or MATLAB. Dynamic Studio contains direct links to MATLAB and Octave, so you can directly import data or export from MATLAB. And this is very typical in research. Yeah? So you use some scientific tool, for example, PIV, to acquire some data, you process them, and then you post-process them in a third-party software to extract something which is meaningful for you, or which is the goal of the research. So the idea here is to, during this lab course, to teach the students the entire pathway of research. And for example, in this case, the flow rate is 42, which is the answer to everything. Right. So what is the performance of Edu PIV when compared to standard PIV systems? So on this plot, on the left-hand side, you can see speed against flow field, and standard PIV, so research-grade PIV equipped with a laser operated in double frame mode, can measure speeds of exceeding 1,000 meters per second. The fields of view can be larger than meter times meter, and the acquisition rate can be typically smaller than 25 Hertz, which means that you would get 25 velocity vector maps per second. Standard PIV can be also operated in a single frame mode. However, in this case, the maximum measurable speed is about 0.01 meter per second, and the other parameters are the same. High-speed PIV. High-speed PIV is typically used to get more information more temporal information from the flow. So as you can see, the acquisition rate is considerably higher. We can get up to 25,000 hertz, so 25,000 velocivector maps per second. But also the lasers are less powerful. So the maximum field of view is a little bit smaller, typically smaller than 0.4 times 0.4 meters. But the maximum measurable speeds are still well over 1,000 meters per second. However, typically TRPIV systems are used in a single frame mode to get temporal information of some vortex tracking and so on. And so TRPIV operated in a single frame mode. We can measure speeds of 200 meters per second. The field of view is the same, and the acquisition frame is actually doubled. So it would be 50,000 hertz. So how does Edu PIV compare to this? The maximum Edu PIV can be operated only in a single frame mode because we have a continuous source of illumination, so CW LED source. So the maximum speed is about 0.3 meters per second. The field of view is about 0.2 times 0.2 meters, and the acquisition rate is about 165 hertz. So the only thing that is not really shown on the plot on the left is what is the meaning of this acquisition rate. So imagine that we have an experiment where we are looking at droplet detachment. For example, in this example, it's in some microfluidic device, and we will record it. So droplet detachment is quite fast process, and we will record it with a 15 hertz camera. Well, with 15 hertz camera, we actually cannot really capture this fast process, so we'll just get a snapshot of what's going on. If we use slightly faster system, so 100 hertz system, we can already see that there's some kind of dynamics, but there's still not really any understanding in what's going on. 1000 hertz system could already give us some insight in the droplet detachment, but still there's still not enough temporal information about the dynamics. But if we used really high speed TRPIV system operated in a single frame mode, so here we have a recording at 20 kilohertz, we can see the full dynamics of droplet detachment. So the main difference between standard PIV and high-speed PIV, that standard PIV is really great for statistics measurements. And the reason is because we can acquire for very long period of time, so to give statistically convergent data. However, TRPIV is great, on the other hand, for tracking of high-speed phenomena. But it's not so great for statistics because we cannot really acquire for a very long period of time because the amount of data generated is very large. So finally, let me introduce Edu Stereo PIV, which is a system which we launched very recently. So as I mentioned in one of the initial slides, Edu PIV is 2D 2C. Edu Stereo PIV is 2D 3C, where we can measure all three velocity components in a plane. And the students would learn additional skills. So in stereo, Edu Stereo PIV, we use two cameras. So it's the alignment of the two cameras to get perfect overlap. It's an adjustment of a Scheimpflug angle to adjust the depth of the plane of depth of focus, or the focal plane, and then also some additional post-processing characteristics. So let me conclude. So Edu PIV is a turnkey solution for teaching laboratories. What is included in the kit is PIV camera with a lens, or two cameras with Edu Stereo PIV. There is LED illumination with LED sheet optics. There's a simple experiment, which is water tank, water pump with a 3D printed nozzle, and everything comes on a support and it's a mounting frame. It contains full version of Dynamic Studio with 2D PIV add-on or Stereo PIV add-on in the case of Edu Stereo PIV. And there's also an access to online support, including lab courses. What is not included is PC or laptop and some additional network licenses. And just for information, on the left, on the right-hand side, are measurements taken with Edu PIV. So it's just a model of a car and some flow around it. It's actually a model of a racing car. So on the top, you can see raw images. Below it are pre-processed images, so with increased signal to noise ratio, remove background. Then I mask out the car, calculated velocities, and then I did some detailed analysis, which shows streamlines and more detailed focused analysis close to the front wing and the engine intake. So I will give over to Graham for the concluding remarks.
Thank you, Ivan.
So,
very interesting. Thank you. Well, I hope you found Ivan's presentation on the PIV technique and Edu PIV of interest. And to complement this, our head office are going to support all webinar participants with a price reduction of 10% for any Edu PIV orders received before the 30th of November. And so to access this special offer, please contact your local distributor and he or she will advise you. And essentially, you can also give them the discount code of WebEdu21 as a reminder if they're not familiar with it. Thank you very much, Ivan. Have we got any questions?
Yeah, so I'm reading through it. So the first question is whether seeding particles are included with the system or if they have to be purchased separately. Yeah, I forgot to mention it. So seeding particles do come with the system. These are 50 microns PSP, which is polyamide, it's nylon. And the quantity is 250 grams. Just for information, when I was doing PhD, I was using about, during my experiment, there was about 500 liters of liquid, and I was using about 8 grams of seeding particles. Yeah. So this 250 grams of PSP that come with the Edu PIV system will last for very, very, very long time. My expectation is more than a couple of years. There is another question. The question is that we mention a number of different systems, CTA, LDA, and PIV, and what is the difference between them, because they are all used for velocity measurements. So, yeah, that's a good question. So the main difference in these three techniques, so CTA, LDA, and PIV, is that they provide slightly different information. Or it's the way how the measurements work. So if we look, for example, at the spatial resolution, the spatial resolution is the highest for CTA, it's slightly lower for LDA, and it's considerably lower for PIV. Yeah? So for CTA, you get more information, more detailed information about the flow structure. But also temporal resolution is the difference. So CTA has the highest temporal resolution. You can acquire it up to 400 kilohertz. Then you have LDA, about 100 kilohertz, and PIV, where acquiring at 1 kilohertz is already a challenge. So you get more temporal information about the flow with the point techniques. On the other hand, CTA and LDA are point techniques. CTA is even intrusive point technique, where LDA is a non-intrusive, and PIV is a global technique. So it gives you overall snapshot of the flow. So all these techniques are complementary, and they have their advantages and disadvantages.
I see we've got one more question, Ivan. Can we actually mount a complete system underwater? I think I'll let you address that one.
Underwater?
Yeah.
Well, Edu PIV, no. But we have systems that are, we have underwater systems. We have LD, underwater LDA, underwater PIV. A few years ago, we installed a stereo underwater PIV here in the UK at Kinetic. So in this case, everything is actually enclosed in some kind of watertight compartment. And in the case that I mentioned that we installed, this was installed on a towing tank. So the entire Edu PIV is actually also Edu PIV. The entire underwater PIV system is dragged through water and is used to measure flow structures underneath ships. But there's no problem to actually do measurements underwater or to mount the system underwater, but it comes at considerable additional cost because all these housings are custom made.
Thank you, Ivan.
So there's a question about whether the recordings of these videos will be public. Yes. So after the webinar, once the videos of this webinar is processed, we'll send the links to all the participants.
Okay, well, I think I'll wind it up at this stage as we have no further questions. Just like to thank everybody for participating, and I hope you can join us for future webinars. Please keep an eye on our website where the next webinars will be publicized. Thank you very much for your time. Hope you all have a good day or a nice evening. Goodbye.
Thank you very much. Take care.
You.
Bye. Namaste.